Hi everyone. Today we'll learn how to determine where a given function is concave up and where it is concave down without seeing its graph. In the first exercise, we need to analyze the behavior of the first and second derivatives of the following two functions. If you would like to try this exercise on your own, stop the video now. You can download these notes using the link in the video description. The first function, the first graph, is concave up. Note that no matter where you draw a tangent line, the function will be curving up away from the tangent line. The first function is increasing. No matter where you draw a tangent line, that tangent line will have a positive slope, which means that the first derivative is always positive. What's more, if you draw a few tangent lines, you will realize that their slopes get bigger and bigger. The last tangent line I drew is definitely steeper than the first one that I drew. This means that the slopes get bigger and bigger, which is equivalent to saying that the first derivative is getting bigger and bigger. The first derivative is increasing. What about the second derivative? The second derivative tells you what happens to the first derivative. If the second derivative is positive, that means that the first derivative was increasing. If the second derivative is negative, the first derivative was decreasing. We know that the first derivative here is increasing, which suggests that the first derivative gets larger and larger, so the derivative of that derivative should be positive. The second derivative is positive. The second example is an example of a graph that is concave down. This graph curves down away from any of its tangent lines. This function is decreasing, which means that its first derivative is negative. What's more, the slopes of those tangent lines get smaller and smaller. The first derivative is decreasing. Because the first derivative is decreasing, the second derivative is likely negative there. We just realized that the first function, which was concave up, had a positive second derivative. The second function, which was concave down, had a negative second derivative. This holds in general for any concave up function and any concave down function. If you are given a continuous function on the interval AB, then if the second derivative is positive on an interval AB, then that function is concave up on that interval. And if the second derivative is negative, then that function is concave down on that interval. What happens then when the second derivative is 0 or the second derivative doesn't exist? When the second derivative is positive, function is concave up. When the second derivative is negative, the function is concave down. When the second derivative is 0 or doesn't exist, that is the place where the function can possibly change its concavity, but it does not have to. Take a look at the next example. We have a function that is concave down, concave down, concave down, and then at some point, somewhere here, it becomes concave up, which means that somewhere here, the second derivative must be 0. Because over here, the function was concave down, the second derivative is negative here. Over here, the second derivative is positive. In between, the second derivative is 0. Then I keep going. I have concave up, concave up, concave up. And I see a corner here. A corner indicates that the first derivative doesn't exist. Because first derivative doesn't exist, the second derivative also doesn't exist here. And look what happens at the place where the second derivative doesn't exist. The function goes to concave up, and then continues being concave up. What about here? The second derivative doesn't exist because the first derivative doesn't exist there. And in this case, the function changes from concave up to concave down. This says that when the second derivative is 0 or doesn't exist, the function can, but doesn't have to change its concavity. Those places are simply candidates for where the function changes concavity. Let's use this fact and solve the next problem. We must find the intervals where this function is concave up and find the intervals where this function is concave down. And also, we must find all the inflection points. If you would like to try this problem on your own first, stop the video now. To determine where this function is concave up and concave down, first I need to find the possible points where the function changes from concave up to concave down and vice versa. And we just said that the function possibly changes from concave up to concave down in places where the second derivative is 0 or second derivative is not defined. Let me then find the second derivative. The first derivative is 4x to the third power minus 12x. Second derivative is 12x squared minus 12. My goal is to now ask myself, are there any places where this second derivative doesn't exist? And are there any places where this second derivative equals 0? This is a polynomial, which means that the second derivative always exists. The first condition gives us no candidates for change in concavity. To set this second derivative equal to 0, first I take 12 out and I get 12x squared minus 1 equals to 0 or equals 0. And then I continue factoring and I get 12x minus 1 x plus 1 equals 0, which means that there are two x's for which the second derivative is 0. It is x equal to 1 and x equal to negative 1. Let's draw the x-axis so we keep in mind where those places are where concavity could possibly change, at negative 1 and at 1. I need to determine now what is the value of the second derivative in between those points. Is it positive or negative? Because if it's positive, that will mean that the function is concave up. If the second derivative will be negative, that will mean that the function is concave down. Again, I have two ways of doing it, method 1 and method 2. Method 1 says, create a table. In the first column, you will have the intervals. The intervals created by those points are negative infinity to negative 1, the interval from negative 1 to 1, and the interval from 1 to infinity. In the second column, you will create test points. The test points are points from each of the intervals. Any point in the first interval could serve as a test point for that interval. For example, negative 2 is there. In the second interval, 0 is there. In the last interval, 2 is there. In the last column, we will determine the sign of the second derivative. When I plug in negative 2 to my derivative, I will get 12 times a negative number times a negative number. Negative times negative gives me positive. That gives me a positive number. The second derivative on the first interval is positive. When I plug in 0 to my second derivative, I will get positive number, negative number, positive number. Positive, negative, positive gives me negative. Finally, when I plug in 2, I will get positive number, positive number, positive number. Altogether, I get a positive number. This means that on the first interval, the second derivative was positive. On the second interval, the second derivative was negative. And on the last interval, the second derivative was positive. This means that on the first interval, the function was concave up. On the second, concave down. On the third, concave up. Method 2 is similar, but it's asking you to draw the second derivative instead. You start by drawing x and y axes. You know that the 0 places of the second derivative are negative 1 and 1. And you also know that the second derivative will curve up. It will be a parabola opening up because the number in front of x squared is a positive coefficient. This means that the second derivative looks like the following. Note that this graph is positive between negative infinity to negative 1 and 1 in infinity, which is exactly what we said in the table. And this graph is negative, it is below the x-axis between negative 1 and 1, which is exactly what we got from the table as well. This means that this function is concave up on the first interval, which was negative infinity to negative 1, and the last interval, which was 1 to infinity. this function was concave down on the interval in the middle, which was -1 to 1. We were also supposed to find inflection points. Now that I know where the function is concave up and concave down, I also know where the function changes concavity. I have a concave up function and I change concavity at -1. And again, I change concavity at 1. So to find inflection points, I already know the x coordinates of my inflection points. My inflection points will have coordinates x coordinate -1 and x coordinate 1. What will be the y coordinates? Well, I need to plug in those numbers into the formula of the function. When I plug in -1 to this expression, -1 to the 4th power is simply 1. If I plug in -1 here, I get simply 6. -1 squared 1 is 1 times 6 is 6. So I get 1 minus 6, that gives me -5. When I plug in 1 to this expression, I will get 1 squared, 1 to the 4th power, that's just 1, minus 6 times 1, that's also 6. 1 minus 6, that's also -5. The inflection points are -1, -5, and 1, -5. These are my final answers.